Hello everyone. So we are back with D and F block elements once again. So here we are going to continue with the properties. It's a continuation of my previous videos. So we move on to next very important property of oxidation state. Very important question is, why do transition elements show variable oxidation states? That's important board question. So variable oxidation state means one metal is going to exhibit more than one oxidation state. So very important reason is when they ask the question why, it's because of the participation of N-1D and Ns electrons in the bond formation. That's the statement which you need to quote if they ask you why do transition metals show variable oxidation states. Okay, now another important thing is the elements which are in the beginning of the series, they exhibit only few oxidation state. That is because they have a very less number of unpaired electrons in the d orbital, like scandium, titanium, vanadium. Whereas the elements in the middle of the series, specifically the element which has exactly half full d orbital, and that's in the first d series, that is 3D series, it's manganese. So manganese show oxidation states from +2 to +7. So why is it? Because it has maximum number of unpaired electrons in the d orbital. So what is the most important thing you can understand here is the number of oxidation state. I'll write it down here for you. The number of oxidation state is directly proportional to the number of unpaired electrons. Okay, number of unpaired electrons in d orbital. So more are the number of unpaired electron, more number of oxidation states that particular element is going to exhibit. Like for example, I told you manganese. Okay, now what about the elements placed at the end of the series? So the elements which are at the end of the series again exhibit very few oxidation states. Why do they exhibit few oxidation states? Again, because the electrons start pairing now. So the number of unpaired electrons in the d orbital would decrease, because now what has started? Pairing of electrons. So that's about your oxidation state. Now the next topic we are going to discuss here is standard electrode potential. That's very important topic. Okay, this topic you are aware of it because in grade 11 you have learned about redox, chapter called as redox. In that chapter there is a discussion of how the electrode potential describes the oxidation or the reduction of a particular species to happen. So here you have to remember a very important thing is, I'll just underline it for you, I will not highlight it. It's E naught. E naught means electrode potential. And remember, this concept you will be also learning in the chapter of electrochemistry, right? So understand it very carefully. Whenever we talk about E naught cell, that's the electrode potential. This electrode potential actually is described only in terms of reduction potential. Okay, so it's a convention in chemistry that the electrode potentials should be written in the terms of reduction. If it is written in terms of oxidation, okay, then take the negative of that sign, it becomes your oxidation potential. For example, here you can see, how do I understand whether the potentials given to me are reduction or oxidation? This will help us to understand. how do I conventionally represent it? It is M2 plus slash M. That means 2 state is getting reduced to 0 state. So it's a reduction because the decrease in the charge means reduction. The increase in the charge means oxidation. So all these potentials given to me here in this data which is there in front of me, it's reduction potential. First thing is that to read whether it is reduction or oxidation. Understood? Now, in case I want to change or I want to know their oxidation potential, how do I do that? So just I said reverse the sign. If it's negative, make it positive. If it's positive, make it negative. So for vanadium, the reduction potential is minus 1.18. That's the reduction potential. If I ask you what's the oxidation potential, you're going to tell me it should be plus 1.18. Did I make it clear to you? Hopefully yes. Now let's discuss copper. Copper has a positive value of reduction potential. If I ask you what's the oxidation potential of copper, just reverse the sign. So positive becomes negative, negative becomes positive. So here for copper it's plus 0.34. So its oxidation potential should be minus 0.34 volts. You remember the unit for potential is volts. Okay. So this is very important to understand. Another very important thing I have written down here, lower the value of E naught reduction. Okay. More stable is the oxidation state. Why so? Now, another very important thing you need to keep in mind, I will use this space for you. If E naught reduction is positive, that means that species has an ability to undergo the process of reduction. That means more easily it has an ability to reduce itself. Okay. So tell me, you have learned already in grade 10 also and in grade 11 as well. If any species has an ability to undergo reduction by itself, it is going to act as an oxidizing agent. Is it or not? So positive E naught, I repeat, positive E naught value signifies that that particular element has an ability to undergo reduction more easily of itself. So if that element undergoes reduction of itself, it is going to act as an oxidizing agent for others. So it acts as an oxidizing agent for the other elements. That's very important thing, and that is what is meant by this particular statement, that lower the E naught reduction. Now understand, I said now here lower. Lower means it doesn't have an ability to reduce itself very easily. Okay. So if it doesn't want to reduce itself, which state will it exhibit for itself to be more stable? Definitely the higher state. And all higher states are oxidation states. Therefore, the more stability goes for the higher oxidation state of such metals which have the lower value of E naught reduction. Now, let us understand this statement. Indeed, I must tell you, we should apply this statement looking into this data. So, in this data, you have clearly understood the concept of E naught reduction. What can you read from this data about copper, about manganese, about vanadium, and about nickel as well? So we know, hopefully you all know, that -1 is greater than -2, right? So if I ask you which element amongst these, okay, amongst these possess the least value of E naught reduction? What's your answer? I repeat again. Which element amongst these possess the least value of E naught reduction? So the least value goes for, yes, I'll give you 1 second time to think. Yeah. Okay, here we go. So very true, it's manganese. Let me use this red one. It's manganese and vanadium. Okay, because their electrode potential is minus 1.18, and I said, remember the concept that minus 1 is greater than minus 2 because of negative sign. Now if I ask you which species has the highest value of reduction potential, yeah, take your time to think. Of course, yes, good, that it's copper. Because for copper, electrode potential, that's the reduction electrode potential, is positive. So it's the highest amongst these elements. But if I ask you which has more negative reduction potential, okay, so then what is your answer? So in the negative sign only I'm asking you to compare. So just don't think that copper is there in the series. So let me just highlight this for you. I'm not asking for copper. Leave copper. Okay. So amongst all these, that is from vanadium to nickel. Now tell me. Yes. More reduction potential amongst these vanadium to nickel goes for nickel. Okay, because minus 0.25 value is higher than minus 1.18. So nickel has more ability to undergo reduction than manganese and vanadium. Okay, but copper has the highest amongst all. So this is very important concept to understand. Okay, now let us discuss few points over here I have mentioned. Now when we talk about manganese, manganese has a configuration of d5. That means it has exactly half-filled d orbital with 5. But if I ask you to write the configuration for manganese, let me write it down here for you, only for manganese. So you're going to tell me 1s2, 2s2, 2p6, right? Then 3s2, then 3p6, 4s2 and 3d5. So since 5 electrons are sitting in d orbital, that means it is very much stable, exactly half filled. Now which state or when can this manganese become more stable? Okay, in other words, I am asking you to give me the oxidation state of manganese in which it shows its maximum stability. So what should be your answer? Yes, your answer should be Mn plus 2, because if I want to write the configuration for Mn plus 2, that means 2 electrons have to be taken out. So outermost shell is used for such a thing, okay? Though 4s is being filled first or before 3d, yet if you want to remove the electron, it has to be removed only from the valence shell. So what should be the outer configuration for Mn plus 2? This everything remains same till 3p6. So 6, 7, 8, from here to here we can write in terms of inert gas also. Count 6 plus 2, 8, 8, then 9, 10, 16, okay, 18. So 6 plus 2, 8, plus 2, 10, 10 plus 8 is 18. And 18 stands for which inert gas? Yes, it's argon. So I can also write it as argon. Okay, so in the books it must be written like that. So please don't get confused. It's nothing but they have picked it here. So argon, and then here it becomes 4s0 3d5. That's the configuration for your manganese. Okay, so therefore, which state of manganese is more stable? The answer for that is Mn plus 2 state. And I already explained you, because here 2 electrons will be lost and D is yet left with 5 unpaired electrons attaining maximum stability. Likewise, Zn plus 2 state is also very much stable. Same thing, D is going to have 10 electrons, which is completely filled octet. So all these points you should be very careful. Now another very important question is, so here I have highlighted this one, Mn plus 2 for you with D5 configuration, D10 configuration for Zn2. Okay, the last one to discuss is Fe plus 3. Okay, Fe plus 3. Now write down take your notebook and write down the configuration for iron. Yeah, I will use this space to discuss. Yeah, so let's get started with iron. Yeah, iron is 26. Atomic number is 26. So the configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d6. Okay, now iron is not stable because there is no stability observed here. So what should I do? I should find a state in which the iron becomes more stable. That is, I have to pick. You know that iron can only exist in two states. That's ferrous state, Fe plus 2, and ferric state, Fe plus 3. So I have to make a choice between ferrous and ferric state. Tell me, what according to you should be the answer of this question if I ask you which state of iron is more stable? Yeah, just 1 second time to think. Yeah, tick tick 1, tick tick 2 and tick tick 3. So here we go. Yes, the answer is right. It's ferric. Okay, why ferric? Now understand it carefully. If I want to write the configuration for ferrous, first let me take ferrous. That is Fe plus 2. So I can't write 26 here. 2 electrons have been lost. So it becomes what? 24 for me. Okay. So I have to fill 24 electrons. So as I told you, the electrons are going to be removed from the outermost shell. That's 4s. So here I'm going to put 0 for you. That's the configuration for ferrous state. What about ferric state? Ferric state means one more electron has to be lost. So I'm going to use the same principle of argon, writing argon till here. Okay, as we did before. 4s0 still it is there because I have to remove 3 electrons. So 2 will be lost from 4s and one more will be lost from 3d. So 3d becomes 5. See here. 3d becomes 5. That's exactly half filled. So it attains a stable configuration. Hence, out of ferrous and ferric, it's ferric state which is more stable. That's another important board question. This chapter is very important for reasoning based questions, and they are definitely going to pose such type of questions. So if your concept is clear, then only you can answer this. So we are done with electrode potential, and that was all what I wanted to discuss with you. Now here I have FAQ for you, which I want you to do yourself. So please read the question carefully and answer. Now my question is, this data is given to you. So using this data, you have to comment whether Fe3 plus state will be stable in comparison to chromium 3 plus or manganese 3 plus. So how do I decide? It is obviously decided on the basis of electrode potentials we have already discussed. And all these electrode potentials are given to you in volts. Now listen here, we have to pick chromium. We have to pick chromium 3 plus, okay, manganese 3 plus and Fe plus 3 state. Can you understand from their electrode potential? So amongst these three, which species has more value of reduction potential? Again, it's a reduction potential. Hopefully you can understand from the data, because 3 state is getting reduced to 2. Okay, so it's a reduction potential. Fine enough. So out of these three, I found that chromium 3 plus has a negative value of reduction potential. That means it doesn't like to undergo reduction. Understood? So since the reduction potential was negative, and for manganese 3 plus it is positive, for iron 3 plus also it is positive. So yes, these two would somewhat like to get reduced, but chromium hates it. Chromium doesn't want to get reduced because its reduction potential is negative. So is chromium 3 plus state stable? Yes, because it's the higher state. It dislikes to reduce itself to plus 2 state. Therefore, chromium 3 plus state is the most stable state amongst these. Now next, we have to make a choice between these two, manganese 3 plus and ferric 3 plus. Now obviously ferric 3 plus has a lower value of reduction potential than Mn3 plus. That means Mn3 plus is the one who happily wants to get reduced because its reduction potential is more positive. So if it happily wants to change its state from plus 3 to plus 2, will its plus 3 state be more stable? Of course not. So the least stable state is manganese plus 3. Okay. And in between we have to fit in our ferric, that is Fe plus 3. So this is the decreasing order of the stability of higher oxidation states. Not decreasing, sorry, it's the increasing order of your higher oxidation state. So amongst all these three, chromium 3 plus state is the most stable state. So I'll write here, it's the increasing order of stability. Okay. So that's important, very very important board question. This is how we have to crack such questions. So let us go ahead. Okay, so here also I have mentioned the same answer. That's the increasing order of their stable oxidation states. So very important point we have discussed here. And this point I have already discussed about oxidizing agents and reducing agents. Okay, let's discuss magnetic properties without wasting any more time. Okay, when we talk about magnetic properties, magnetism means you have learnt again MO diagrams, of course, that is molecular orbital diagrams. Okay, so when we have learnt these MO diagrams, we have already learnt that if unpaired electrons are there, it's paramagnetic, and all molecules with paired electrons are said to be diamagnetic. And we have discussed in the beginning itself that all transition metals are said to be true transition metals when they have unpaired electrons in their d orbital. Okay, so d orbital is very very important, as it should possess unpaired electrons. Right. So what do we understand from this? We very well understood that paramagnetic behavior is evident in transition metals, and more are the number of unpaired electrons, higher will be its paramagnetic behavior. Point number one. Second thing is, as we move from scandium to chromium, the number of unpaired electrons increases, right? So magnetic behavior will also increase. Obviously, I'm talking about paramagnetic behavior. So how do I calculate the magnetic moment now? So magnetic moment is calculated by a formula. Mu is equal to under root n into n plus 2 bm. Bm is Bohr magneton, that's the unit, where n stands for the number of unpaired electrons. Okay, n stands for number of unpaired electrons. So that's magnetic property. Now let me just finish off with this property as well as catalytic property. So all transition metals act as a good catalyst. Reason, there are few reasons highlighted over here, but the most important of all these is the d orbital. So incomplete d orbital behaves, all these metals behave as catalysts. So catalyst is one of the parameter which is very important to discuss the rate of the reaction. Okay, so catalysts basically enhance the speed of the reaction, and all those elements which have empty d orbitals amongst these transition metals behave as a good catalyst. Like iron, you have heard about, iron acts as a catalyst, nickel acts as a catalyst, right? So why? Because of the presence of unpaired electrons. And of course, variable oxidation state we have already discussed, and they also possess large surface area. So here very clearly it is mentioned. And the last property will be formation of colored compounds. Again, because of the presence of what? Unpaired electrons in the d orbital, these electrons get easily excited to the higher states, that is they exhibit dd transition by absorbing the light of particular wavelength, and the higher state is very much unstable. Therefore when they come back to their ground state, they radiate a color change, and that color will be complementary to the wavelength what they have absorbed to get excited. And again, the formation of complexes is due to the same reason, presence of d orbital and higher charge on cations, that is variable oxidation state. They also have an ability to form interstitial compounds. Okay, so that's another board question. I have written FAQ for you. So transition metals possess large size, we have just now discussed. So they have some voids or gaps in their structure. Thus small elements like carbon, hydrogen, nitrogen and boron can fit into their lattice site, and resulting in the formation of interstitial compounds. So basically it is because of the presence of voids. And they also participate in the formation of alloys. And alloy, it's a mixture of homogeneous mixture of a metal with a metal, another metal, or a homogeneous mixture of a metal with a non-metal, right? So here I have highlighted 3 alloys for you. You need to learn the composition. That's very important. They can ask you in board exam. So we have discussed all this, and this disproportionation reaction I would like to discuss in next video. So we'll end up here. Any doubt, get back to me in the next session. Thank you and learn.